let's get started here, right?
Yeah, let's get started.
I love it.
We're enthusiastic today.
Good, because I am exhausted by now. So I'm going to rely on that energy.
Thanks for getting our test grades in. That made me really happy. That was some speedy grading.
This is an easy one to grade.
Was it?
It is.
Oh, yeah.
Because there's not like it's real easy to check
Yeah.
for me.
There's like one.
Well, it's not so much that, it's the work. It's
Yeah.
like, it's easy to check the work because it's like, did you set it up? Okay. Did you get to the end with the right thing going into the calculator? No or yes. And then like, okay, so it's just like a calculator thing. All right, that's easy. You know.
Did you take points off for rounding?
Not really.
Okay, good. What about
So I was
labeling?
labeling.
Like the inch centimeters.
Oh no, I didn't. Yeah, I probably should have, but I didn't. Probably next class. I have 2 people that are, I think, set to take it on Monday. So we won't see you guys again until Tuesday, and I should be ready to, assuming that everybody makes it on their scheduled makeup day, we should be good to go. All right. So last time we were in this chapter A, we had talked about solving systems by graphing and then solving systems of inequalities by graphing. Did you guys have questions from the homework, or can we just do 1 or 2 of these just for refresher?
I can do it.
What do you say? Let's grab that. Anybody have a preference on 1 through 8? Okay, you just want Mr. Kulik will just pick. I'll be nice and I'll pick 2 even ones. Look at that. Why did I pick even ones? Yeah, because you already have the answers for the other ones. Okay, so if we're going to solve a system of equations by graphing, I'm just going to create an XY table for each of the 2 equations. I'm going to plot these things on the XY axis and look for the intersection, right? So to plot an equation for a line, how many points do I need? 2. Does it matter which values for X or Y I pick or use? No. So I'm just going to pick stuff that's convenient. So I'll pick X to be 0. If I plug 0 in for X, what do I get for Y? 2, right? 5 times 2 is 0, plus 2 is 2. And then maybe I'll pick, oh boy, let's do maybe -1 for X. What do I get for Y then? -3, very good. And we'll do the same thing over here. So I'll pick 0 for X. When I plug that in, what do I get for Y? 0. Then maybe we'll pick 2 for X. What do I get when I plug that in? 6. Okay. Achoo! Ooh. Thank you.
Bless you.
Thanks. Okay. So I'm going to plot this one in blue, and I'll plot this one in green. So each grid line is just going to be 1 unit. So I have 0, 2, and then -1, -3. That looks pretty good there. Okay. Go away for a minute. Do the other one. So I have 0, 0, and then I have 2, 6. 1, 2, 1, 2, 3, 4, 5, 6. Come back, ruler. That looks pretty good. So if I look at this, the intersection of these two looks to be maybe right here at -1, -3. Everybody buy that? How can I check to guarantee it? Well, if I take my first equation and I plug in -1 for x and -3 for y, well, that satisfies it because -3 is -5 plus 2. If I take my second equation, and I plug in -1 for x and -3 for y, well, -3 is 3 times -1. That satisfies it. So I'm 100% that that is my solution. Everybody feel good on that? If you're doing this by hand, what do we have to be careful about? Neatness is going to count here, right? It's going to be tough to find the intersection correctly if you've got if you don't have equal mark tick marks and you have like a crooked X and Y axis. So doing this in OneNote where you can have the graph paper in there and use the ruler function, super helpful, at least for me. All right. And then let's look at what's that other one called? 6, I said. Let's do that one real quick here. So much the same way. I'm going to graph each of the two inequalities. But to do that, before I do that, I want to write these so that the y is by itself. That's going to be really important to me so that I know how to shade my inequality. So to get the y by itself from this first equation, first inequality, what do I have to do? Subtract 3x to start. Notice that the inequality symbol doesn't change when I add or subtract things from both sides. What do I have to do next? Divide by -1. Notice when I do that, though, the inequality symbol switches direction, right? It goes from greater than to less than. All right. So now I'm going to go ahead and just treat this like an equation. And I'll pick some values for x. I don't know, let's do 0. If I pick 0 for x, what do I get for y? Anybody? -12. You just shout them out if you know. You don't have to whisper it as quietly as you can. And then maybe let's pick 2 for x. When I plug 2 in for x, what do I get? -6. Great. All right, let's go on to the other one. We're going to do the same thing. I get the y by itself. So I'll add x to both sides. Oops. And then we'll divide by 8. Since I'm dividing by a positive, my inequality symbol doesn't change directions. Everybody's good there? All right. All right, let's pick some values for x. My goal here is to not end up with a stinking fraction. So 4 seems like a good value of x to pick, because what's 4/8 the same as? 1/2, and a half plus a half is just 1. And I'll do -4 as my other choice, because -4/8 is -1/2, and -1/2 plus +1/2 is just 0. Now, could I have done something else and end up with a decimal? Sure, but if I'm trying to plot this, that makes it a little bit harder to be accurate, right? So, like, technically it doesn't matter, but like, for Mr. Kulik, who's not a naturally neat person, it matters to me. So I'm going to try to pick my x's so I don't have any decimals there. You know what I mean? All right, let's see here now. I got a lot of vertical here to deal with. And again, we're going to do, we'll do green for this first one, and then blue for this second one. Oh, I thought I said blue for this second one. All right, so 0, -12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 2, 6. 1, 2, 3, 4, 5, 6. My ruler out there. Ooh, that's pretty close. All right. Okay. Go away, ruler. Give me that blue. So 4, 1. 1, 2, 3, 4, 1. 4, -4, 0. 1, 2, 3, 4, -4, 0. Get my ruler back out. Oop. Oh no. My poor calculator. Don't worry, guys, they're drop tested. They really are. Texas Instruments like drop test them for like, so they shouldn't break inside of like, I don't know, they're like 5 feet or something. I forget what the protocol is. I read it at one point. I was curious. Oh no. Oh no. Oh no, Mr. Kulik. 1, 2, 3. Okay. It's probably pretty good. Here we go. Okay. So to me, it looks like the intersection is like right there, which is, what do you guys think? Oh, I'm dumb. I don't care what the intersection is. What are we doing here? These are inequalities, right? So I did this wrong. What did I do wrong? It's not the flipping. When I drew the line, should have been dashed. Ah, Mr. Kulik. I'm upset too, guys. Ugh, hold on there. There we go. Ah. Okay. And same thing with the bluesies, right? Because those should have been, that should have been a dashed dirt. What was it? It was like 7 degrees or something I had. Good enough. Okay. Right out of there, ruler. Okay. So that, again, because they were not or equal to inequalities, that's why I used a dashed instead of a solid. So for a greater than, I'm going to be shading above my line. For the less than, I'm going to be shading below my line. So the intersection of those two regions is going to be that little V there. So that's where my coloring should be. Any XY from that region, if I plugged them into both inequalities, should satisfy the inequalities. Does that feel okay, guys? Okay. Again, it'd been several days since we'd done one of these, so I figure coming back and talking about it again would be helpful. And plus, we just did 2 homework problems. If you haven't done them yet, it's 2 done. Yay! All right. Let's pick up with the new stuff here. So today we're going to be doing sections, we'll do section 3, and we'll probably start some of section 4. So in section 3, we're going to be talking about, where's my thing? There you are. Boy, that is not big enough. Oop. We're going to talk about solving linear systems algebraically. So previously, last time we met, we talked about solving systems by graphing, right? What's the big downside to graphing? We just kind of talked about it. So neatness counts, right? If you draw a messy picture, you're probably not going to get the answer. And that becomes even a bigger factor if your answer is a kooky decimal. So imagine our actual answer is like 3.26 comma negative 5.92. Imagine how accurate of a graph you'd have to draw to get that solution. So each tick mark would have to be like 100th. So you need like 100 tick marks for 1 unit to get an accurate enough picture out of this, which to me just sounds like just an incredible nightmare, right? You guys see what I'm saying? Yuck, Aruski. So in practice, we're really never going to use graphing to solve a system if we're given the choice. The only time we would use this is if all you're given was like, here's a picture of the 2 functions, solve the system. In which case, okay, all I have to do is look for the intersections. Like, whoop-de-de-doo. But if I'm actually given equations for these, I would do this algebraically. There's 2 algebraic methods that we're going to talk about here. The first is called substitution. So the way substitution works is you're going to pick one of the two equations. It doesn't matter which one. And then after you've picked that equation, you're going to pick a variable. It doesn't matter which one. You're going to isolate that one variable and then substitute that into the second equation, thus eliminating a variable in the second equation, which you can now solve just like you would in Algebra 1, just like a one-variable equation. You'll get your answer and then plug it back into one of the two-variable equations to get the other. Let's do a numeric example to kind of drive that home. Bless you. You're welcome. Okay. So in general, it does not matter which equation you pick and which variable you solve for, or the variable you isolate. But in practical terms, it can make the problem a lot more tedious if you're not being careful about this. So in general, how do I choose the equation and the variable to isolate? What I'm looking for is I don't want to make any fractions doing this process because that just complicates life in general, right? So what I'm looking for is which equation, which variable is going to allow me to isolate it without having to do any division. Or if I have to do some division, I want the division to go in evenly so that I don't have any fractions. So with that in mind, looking at what we have here, there's an obvious choice. Which equation and which variable would I want to isolate? I'd want to pick equation 2, and I want to isolate the x. Because I can do that without having to do any division, so there's no chance of me generating a fraction. Because that just is going to make life more complicated. I'd like to avoid that if I have the choice. I have a lot of choice here about what I do. So I'm going to pick to make my life easier. My life's hard enough. So to isolate the x, to get x by itself, what do I need to do? Yeah, just subtract 3y from both sides. Okay. It's easy enough. What I'm going to do now is I'm going to take that expression for x and substitute it into the x in equation 1. So if I call this, I'm going to rename these. I hate that I've called them all A's and B's. So I'm just going to take equation B. This new one I'm going to call C. So what I'm going to do is I'm going to take my equation C and plug it into equation A. That's just a little note to myself of what I did, so I can, if I go back and I look at this, I can tell what the heck I did to get these things. So where the x was, I'm going to just plug in that expression for x that I get from equation C. If you look now, my new equation has only y's in it. So that I can solve for really easily. I'll just distribute the 2 through. I'll combine my like terms. Subtract 6 from both sides. And then divide by -1. And I found that y has to equal 11. Does everybody feel good so far? At least you're ready to ask something.
When you take like negative y plus 6 equals 5, wouldn't that be 1?
I'm subtracting 6 from both sides. Yep. It's okay. Look, if you don't see it, you can ask. Even if it's like, oh yeah, I do see it. After you say it out loud, like what just happened. That's okay. Sometimes talking it out is all we need. All right, now that I have the answer for y, I'm going to take that answer and plug it back into c. So I have x equals 3 times, instead of y, I'm going to write 11. So I get that x is negative 30. And what do I do here? To write my final answer, we write it as an ordered pair in x comma y. Negative 30 comma 11. Is everybody okay there? Cool. The other technique that we're going to talk about is called elimination. So in the elimination process, again, what we're going to do is we're going to pick a variable to eliminate. It doesn't matter whether we choose x first or y first. Once we've chosen that variable, we're going to multiply one or both of our equations by some constants, possibly different, so that the variable that I'm trying to eliminate have opposite coefficients. So for example, if one of my equations is now 3x, I want the other equation to be negative 3x. Okay with that idea? Once I've done that, I'm going to add the two equations together. So I'll add the left-hand sides together and add the right-hand sides together. In doing that, the variable that I'm trying to eliminate will cancel out because I'll have like 3x plus negative 3x, giving me 0. And that's going to give me an equation in one variable. I can then solve that variable and then plug it back into one of the originals. Let's do a numeric example to kind of drive this home. All right. So, it does not matter whether I want to eliminate the x first or the y first. But in practical terms, I want this to be as easy as possible. And oftentimes, it does matter which one I choose to eliminate if I want to make this process as easy as possible. And since I have the choice, I could do eliminate x first or y first, it doesn't matter. I want to choose wisely so that the process is as easy for me as possible, right? So what I'm looking for is if I look at the x's and look at the y's and I look at their coefficients, which one is going to be easier to make the coefficients opposites? 3 and 6 or 7 and 8? 3 and 6. I agree. That's what I'm going to choose to do. Okay. So what do I have to multiply equations? I'm going to recall these A and B. A and B by so that the variables or the coefficient on x are opposite. Yeah, I'm going to just take equation A and multiply it by -2, and then we can add it to equation B. Everybody agree with that? So this is just my notation to explain to myself what it is that I did. So equation 2A is going to be -6 plus, or -6x plus 14y equals -20. And then equation B is 6x minus 8y equals 8. And now I'm just going to add down. So -6x plus 6x is 0, which is what I need to have happen. If my variable that I'm trying to eliminate doesn't cancel out, I cannot proceed from this step. You go back to the drawing board and figure out, oh, I should have multiplied by 4 instead of 7 or something, you know. 14y plus -8 is 6. And then -20 plus 8 is -12. So 0 plus 6y, well, that's just 6y. I divide by 6, and I get that y is -2. I'm going to then take that answer and plug it back into either equation A or equation B. Does it matter which one? No. Is one of them going to make it easier than the other to plug this back into? I don't really think so. Right? The numbers are about the same size. They're all going to involve dividing. So, like, who cares? For alphabetical sake, I'm going to plug that into A. So instead of y in equation A, I'm going to put in the -2. So that gives me 3x plus 14 is equal to 10. To solve for x, I'm going to subtract 14 from both sides and then divide by 3. So I get -4/3. So there's my answer, -4/3 comma -2. If I tried to do that by graphing, that would have been rough, right? Coming up with -4/3 as a coordinate, yeah. You might have been able to guess it, but that would have been rough to be that accurate to come up with that. All right, so we should feel pretty good about what it looks like when we get one solution. But there were two other outcomes that I can have for a two-variable system. What else can happen? What are the other two outcomes I can have other than one solution? No solution and infinitely many solutions, right? So if I'm doing this substitution or elimination process, what does it look like when I get no solution or infinitely many solution? So if at the end of step 2, you get something like the following. So step 2, remember, that's after you've plugged your equation C back in, and you're down to one variable, or you've added your equations together if you've done your elimination. If you get something like 0 equals 0, something that's always true, that's the infinitely many situation, infinitely many solution situation. If you get something like 0 equals 1, an equation that's always false, that's the no solution indicator. Okay. Now, when I say something like 0 equals 0, what's another thing you could have gotten there other than 0 equals 0? Like 1 equals 1, 2 equals 2, 17 equals 17. Something like that, right? When I say something like 0 equals 1, what else could have you gotten? 2 equals 3, 7 equals 57. Some other piece of nonsense, right? Something that's always false. Right? It doesn't have to be exactly 0 equals 0 or 0 equals 1, but something like that. Does everybody feel okay about that? Okay. I want to point out one thing that you have to be a little bit careful about when doing the substitution and worried about the infinitely many situations. Okay? So imagine we took equation C, but instead we plugged it back into B. Where did equation C come from? Equation B. If I plug B back into B, what's going to happen? I'm going to get 0 equals 0. Does that mean that this is infinitely many solutions? No. You have to plug C back into the other equation. So be careful about that. It's very easy to make that mistake and then assume it's infinitely many solutions when it's not. It's not infinitely many solutions. You made a mistake and it looked like it. Do you guys kind of see what I'm saying? So just be careful. Okay, that you can't plug the equation you isolated the variable with back into itself. Right? So what else is there? Well, what if we had like a story problem, right? Let's take a look at this example. To raise money for new football uniforms, you decide to sell t-shirts. Short sleeve shirts cost $5 each and can be sold for $8. Long sleeve t-shirts cost $7 each and can be sold for $12. At the end of the fundraiser, you determine that you spent a total of $2,500 to buy t-shirts and sold all of them for a total of $4,200. How many short sleeve t-shirts did you sell? All right. This is a pretty classic example of a solving systems problems or solving a system story problem. If you've taken an ACT recently, I would be surprised if you didn't have a story problem that was essentially this kind of a question. This is a favorite type of question. I think Caden said he had ACT class last night and they did basically this exact same problem in that class. So this is the way that, so doing one of these kind of problems, the hardest part is the setup, is translating this into an equation that you can solve. Usually the solving part's relatively easy in comparison. So here's what we're going to do. I'm going to talk about kind of how to do the setup in detail here. So the first thing that I want to do is figure out what are the unknowns here. What are we looking for in the problem? Oftentimes, if you read the last sentence, that's going to tell you. What's the last sentence asking for? How many short sleeve t-shirts did you sell? Well, that's going to be one of my variables. I'm going to use the letter S. Where S is just going to represent the number of short sleeve t-shirts. Now, important in here, we're told that the number of t-shirts sold and the number of t-shirts we bought are the same. So I can just say S is just the number of t-shirts. Everybody's cool with that? Was that the only unknown, though? What is the other unknown? What else don't we know? Did we buy and sell just short sleeve t-shirts? No, we also bought and sold long sleeves. Do we know how many of those we bought and sold? Nope. That'll be my other variable then. And again, since we were told that we sold all the t-shirts that we bought, I'm just going to call L the number of long sleeves. Okay? Next thing I'm going to do is I'm going to go through and identify what these numbers that I'm given in the problem mean. So the first number is $5. What is that $5 representing? Okay, what kind of t-shirt? Okay. So I'll say the cost per short sleeve t-shirt. And the next number I see is $8. What is $8 representing? Okay, so I'll say that's the price per short sleeve t-shirt. Ooh, t-shirts, t-shirt. Spelling counts. The next thing I see is $7. What is $7? Okay, the cost per long sleeve t-shirt. And then I see $12. What's that? It's the price of the long sleeve t-shirt, right? Okay. The next number is that 2,500. What is that representing? What's up? Total. Okay, total what? Cost of all t-shirts, right? Very good. And the 4,200 is a total. Let's call that profit of all t-shirts. Everybody feel good about what all these numbers are representing here? All right. So right away, what jumps out to me is that these two quantities are totals. So I think I'm going to have one equation representing the costs and then one equation representing the profits. So I know the total costs, when I add those all up, between the short sleeve costs and the long sleeve costs has to equal 2,500. Likewise, I know that the short sleeve profits plus the long sleeve profits have to add up to give me $4,200. Everybody's okay with that? How would I calculate the cost, the total cost of just from the short sleeve t-shirts? Well, I know the cost per short sleeve t-shirt, and I know the number of short sleeve t-shirts. So if I bought 5 t-shirts at $5, how much did that cost? $25. How did you get 25? You multiplied the price per shirt by the number of shirts. Everybody, does that feel very natural? So my short sleeve cost is going to just be the price per shirt times the number of shirts. We'll do the same thing then for the long sleeves. The price or the cost per shirt times the number of shirts. Everybody feel good there? And the profits are going to work the same way, right? It's the amount we're charging per shirt times the number of shirts, and the amount we're charging per shirts times the number of shirts. So those are my 2 equations. Now I just need to solve this system. Would you like to use substitution or elimination here? I have a preference. I would use elimination here because if I look, there's no variable I can isolate without getting a fraction, right? Whether I try to get the s by itself in the first equation or the L by itself or the s by itself in the second equation or the L by itself, anything I'm doing is going to generate a fraction. Now, is it okay to do it still? Substitution? Sure. I would not because I don't want to deal with the fraction. So I would do elimination. Matthew? Of course. Is everybody okay with the reasoning why I'm avoiding substitution here? And it's not the end of the world to have a fraction, but like if I have the choice, I just prefer not, right? Like why bother? Okay. So let's do elimination then, because the fractions aren't going to bother me there. Which variable do you want to eliminate first, S or L? I don't think it really matters, but I would pick S also because the coefficients are a little bit smaller. Okay, so if I just call this equation A and equation B, what do I have to multiply to equation A and what do I have to multiply to equation B so that when I add them together, the S's cancel out? 8 to equation A, and then what to equation B? Yeah. Does it matter which one is negative? No. I'm going to put it here just so I don't have the weird plus and negative because I already wrote the plus sign there. But it doesn't really matter. Everybody agree that that'll do it? So negative 8a is going to be 40s minus 56l equals negative 20,000. And then 5 times 8, that's 40s, plus 5 times 12, that's 60l. 5 times 4,200 is 21,000. So when I add down, what do I get? And I'm left with 4L equals 1,000. If I divide both sides by 4, I get 250. To get S, now I'm going to plug L back into either equation A or equation B. Does it matter which equation I choose? No. Does Mr. Kulik have a preference? Yeah. Which one would I choose? I'd plug it back into A because the coefficients are a little bit smaller in equation A than they are in equation B. And I would prefer not to do 250 times, the biggest number possible. So plugging back into A, I have 5S plus 7 times 250 is going to be 1,750 equals 2,500. Subtract 1,750 from both sides is 750. If I divide both sides by 5, I get 150. And there we go. Again, the worst part was the setup, right? This general setup, though, is super, super common for these kind of solving system story problems where you're given, where you have like rate times quantity plus rate times quantity gives you total. That's a very, very common setup for these kind of system story problems. Okay? Super, super common. All right. Blah, 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 blah. Let's do another example. So here, yes, of course, sure, go ahead. In this one, it says solve the system using any method. So does it matter whether I do substitution or elimination? No, it says I can use any method I want. Great. If I'm looking at this and I want to do substitution, is there a good equation variable to choose for substitution? Yeah, what would you pick for substitution? I'd pick equation 1 and solve or isolate the x because as a coefficient of 1, so there's no division needed, no fractions can be generated. That would be good. Would elimination cause any problems? No. I mean, you have the coefficient of 1. I can just multiply equation A by -3 and then add them together, right? Really, elimination you're never going to run into a problem with. If it says to use any method, substitution would be the only one I'm careful about just because I don't want to have to deal with fractions. But elimination is going to be kind of the same no matter what. Everybody's cool? So let's do substitution. That seems like the natural choice. So picking equation A, we'll isolate the x by adding 2y to both sides. And then we'll plug that value for x back into equation B. So we have 3 times, and now instead of x, I have 2y plus 4 minus 6y equals 8. So now I'm just going to simplify things. So I'll distribute the 3 through. I'll combine my like terms. So 6y minus 6y is 0. So I'm left with 12 is equal to 8. What's that mean? No solution. It might not be 12 equals 8, but it'll be something like that. I'd also like to point out to you that if I looked at the x's, I noticed to go from equation A to equation B, I'd multiply by 3. If I look at the y's, to go from equation A to equation B, I'd multiply by 3. But to look at the constants, to go from equation A to equation B, I'd multiply by 2. Do you remember we talked about this last time? That's another indicator that there's no solution when the left-hand sides are a multiple of one another, but the right-hand sides are not the same multiple of each other. So if you notice that squared away, you could just do this to claim no solution. You would not have to go through all the rigmarole we just went to. Now, the odds of you remembering to check for that on the test, maybe not great. But if you did think to do that, you could certainly do that and use it as justification that there's no solution. Cool? All right, one more two-variable problem, and then we'll move on to the next section. All right. Again, it says use any method. So let's start with substitution. Is there a good substitution route here? No, right? No matter what variable I choose to try to isolate, I'm going to end up with a fraction every single time, right? Mr. Kulik's choice, I'm not doing substitution on this. I'm not touching it. I don't want to do the fractions. It's not worth it. I would just do elimination. So, which variable, if we're going to eliminate, would you like to eliminate? X's or Y's? Does it matter? Yeah. Which one would I pick? I'd probably pick the X's because the numbers are a little bit smaller for the X's. So let's isolate the X, or eliminate the X. What would I have to multiply equation A and B by? To isolate the X's, or eliminate the X's. Good. You mean 2, though, right? And why don't either of them need to be negative? Yeah, because one of them's already negative. Exactly right. Yes, perfect. Everybody's happy with how we came to that? 7 times 4 is 28. 2 times 14 is 28. That'll do. If you'd multiplied the equation A by 14 and equation B by 4, would that have worked also? Yeah, sure, the numbers are a little bit bigger. It's a little bit crummier to deal with, but it still would work. All right, so let's go ahead and do that. 7 times equation A is going to be 28x minus 70y equals 56. And equation 2b is going to be negative 28x plus 70y equals negative 56. So when we add down, I get 0 for x's, 0 for y's, and equaling 0. Uh-oh, what does that say? Remember, that was infinitely many solutions is what we say about that when you get something that's always true. Now to clarify, when we say infinitely many solutions, does that mean I could pick any x and any y and that'll be a solution to the system? No, right? Remember, graphically, what this looks like is that like equation A is this line and equation B is the exact same line. So it'd have to be some point on this line. Now there's infinitely many points on that line. That's why there's infinitely many solutions. One of the things that we'll ask you with 3 variables to do is to represent the general solution for your infinitely many solutions. So let's practice that now with a 2-variable problem that's much easier to do. So we want the points x, y that are on that coinciding line, right? So what I can do is I can take my first, either of my 2 equations. Let's just take the first one, for example, and get the y by itself. So I'll subtract 4x from both sides, divide by -10, and I have this. So I can say my general solution is x comma, and instead of y, I'll just write 2/5 x minus 4/5. So this would be like my general solution. And what this is saying is, like, if I pick a value for x, like 0, I can plug it in to get a value for y, and it says that that is an example of a solution. And if I wanted another solution, I could just pick a new value for x. And I could just keep on doing this as long as I wanted, getting more and more solutions. Is everybody okay with that notion? Is this the only way I can write the general solution? No, right? If I go back to that equation A, and this time, instead of getting the y by itself, I got x by itself. I could add the 10y over, and then divide by 4. So instead of writing x comma y, I can write my expression for x in terms of y, comma y. This would also be an acceptable general solution. It would work the same way if as I pick values for y, I could then generate values for x with those choices. Does that feel okay? This gets a little bit more complicated in 3 variables. But we'll deal with that and see some examples when we get to 3-variable systems here in a moment. Okay? Well, not today, but eventually, next time. So in section 4, we're going to talk about solving systems of equations in 3 variables. So what do I mean by an equation in 3 variables? Right? Probably might not have seen that before. So an equation in 3 variables is just something of the form ax plus by plus cz is equal to d. where those three coefficients A, B, and C are not all zeros. So a system of three variables is going to contain three equations, each of which with three variables. And a solution for that system is going to be a ordered triple, an XYZ, that satisfies all three equations. And the solution then is going to be representing a point where those three equations intersect. Well, what's that going to look like graphically, right? When we've plotted the two variable equations, we plot them on the XY axis, which is a plane, right? It's a two-dimensional space. When we plot an equation in a two-dimensional space, we get a line. That's a one-dimensional object. If I'm going to graph something in a three-dimensional space, what's a three-dimensional space kind of feel like? It's like a fish tank, like a big rectangle, right? Where there's length, width, and height. There's three dimensions to it. So when I graph an equation in a three-dimensional space, I'm going to get a two-dimensional object, like a plane. So geometrically, one solution is going to look like something like this, where the red plane is representative of one equation, the green plane is representative of a second equation, and the blue plane is representative of a third equation. And this black dot here is the single intersection of those three planes. Is everybody okay with that? What is infinitely many solutions going to look like? Well, imagine three planes intersecting, but not uniquely, not at just a single point. So again, notice the three planes are intersecting, but their their intersection is now a line. Right? That's what infinitely many solutions is going to look like three-dimensionally. What's no solution going to look like three-dimensionally? Well, I need none of the three planes, or all three planes can't intersect anywhere, correct? But that doesn't mean that none of the planes are going to intersect with each other. There's actually three different no solution situations. Notice here that green and blue intersect, but not red. Red and blue intersect, but not green. Green and red intersect, but not blue. All three planes don't intersect anywhere, but each pair of them do. Or in this one, where red and green intersect, but not blue. Red and blue intersect, but not green. Or the most obvious one is where all the planes are parallel to each other and there's no intersections at all. So this is the easiest no solution one to come up with. You'll get that on your first elimination. These two are a little bit tougher because you probably won't see those until your second elimination. Well, this one you can't see until your second elimination. You might be able to see this one on your first elimination if you had chose to try to add the green and blue planes together. All right. So again, algebraically, for three variables, the techniques, exactly the same, just with minor modification. So we can do substitution or elimination. So substitution is the same procedure, but it's has an additional step. The first step, we pick any of the three equations. From that equation that we pick one variable to isolate. We then take that result and plug it back into the other two equations, creating a two-variable system of two equations. We can then solve that system either with substitution or elimination. Typically, elimination would be easier there. And then it's just like a problem from last section. Let's do an example there, and then that's probably going to be just about it for us. All right, so we're doing substitution here. First thing I want to do is pick an equation and pick a variable from that equation to isolate. Now, it doesn't matter in general, but like it matters to me which one I'm picking because I don't want fractions. So which equation and which variable from that equation should I pick so that when I isolate it, I get no fractions? Anybody see it? There's just one choice to get this. Which equation? 3, and isolating y would be what I would do. Yep. In general, if I see something with coefficient 1 or -1, that's my pony. That's what I want. I'm stopping looking at that point. I found one that'll work. I'm just going to go with it. So to isolate the y, I'm going to subtract 6x from both sides, subtract 4x or 4z from both sides, and then divide by -1. Then I'll plug that into, well, I'm going to rename these A, B, and C to A and B. So when I do that, I get 4x plus 2, and then instead of y, I'm going to write 6x plus 4z plus 1. I have plus 3z equals 1. And when I do it to b, I'm going to have 2x minus 3, and then instead of y, 6x plus 4z plus 1 plus 5z equals -14. Oh boy. Now I'm just going to simplify things down to get to a two-variable system. So I'm going to just distribute things through. And I would point out to you guys, you'll notice that when I'm writing my z's, I'm putting that vertical bar in my z's. If you do not have exquisite penmanship, I strongly encourage you to be doing the same thing so you can tell the difference between a 2 and a z. That is a frequent silly mistake I see students make, is their penmanship gets bad and their z turns into a 2 along the way somewhere. And I hate seeing that, right? It's just like such a silly mistake. We'll combine some like terms. So 4x and 12x is 16x. 8z and 3z is 11z.
Good afternoon. Let us pause
Ooh, that is
reflect
quick.
upon our day. Spend a moment in gratitude for the gifts and blessings of the day. All blessings and gifts come from you, Lord. Thank you for the gifts you have bestowed upon me. Amen. In the name of the Father, and the Son, and the Holy Spirit. Amen. Have a great weekend.
Remind me that we have to finish this next time. Have a good weekend. I'm ready for you guys to go.
I don't have a phone, I can't call her.
Bye, everyone. Oh, reminder, 1 through 8 is due for Sunday. At this point, you guys could probably do, like, what is it, 9 through, like, 26 or something by now, but that's not due till next Sunday, so don't worry about that. Archland, if you have a second, let's get your shared OneNote and stuff for the class. We need to do that still. Totally forgot.